You mentioned binary search right at the start.
Yes, binary search is the payoff. It's a super fast search algorithm, but
It only works on sorted data.
it absolutely requires the data to be sorted first. That ordering is what gives it its power. Trying it on unsorted data just gives garbage
How
results.
does it leverage the sorted order? What's the principle?
It's another divide and conquer idea, but for searching, you want to find a target value in a sorted list.
Okay.
You start by looking smack in the middle of the list. Compare your target to the middle element.
Three possibilities.
Exactly. 1, the middle element is your target. Found it, search over. 2, your target is smaller than the middle element. Since the list is sorted, you know your target, if it exists at all, must be in the first half of the list, so you can completely ignore the second half.
Throw away half the data in one comparison.
Precisely.
Oh.
3, your target is larger than the middle element. By the same logic, you know it must be in the second half, so you ignore the first half.
And then you just repeat the process on the remaining half.
You got it. You take the half you kept, find its middle element, compare, and eliminate half again. You keep having the search space until you either find the target or the search space becomes empty.
Empty meaning the target isn't in the list.
Correct.
The pseudocode illustrates this while not found loop.
Yes. It uses lower bound and upper bound to track the current search range. It calculates midpoint. Then it compares a midpoint with the target X.
If a midpoint X.
The target must be in the upper half, so you update lower bound to midpoint plus 1.
If a midpoint X.
The target must be in the lower half, so you update upper bound to midpoint 1.
And if a midpoint X.
You exit, because you found it at midpoint.
The loop also needs that check. If upper bound ever becomes less than lower bound, it means the search space is empty and the item doesn't exist.
Critical check. That's how the loop terminates if the item isn't present.
The Python code example shows this with left, right, and mid variables really clearly.
Yeah, it's a very elegant and concise algorithm when implemented.
Now the speed. Why is this all gay? That sounds incredibly fast.
It is incredibly fast. Logarithmic complexity means the time it takes grows very, very slowly as the list size increases, because you eliminate half the remaining possibilities with each single comparison.
Right.
You can search through enormous lists with surprisingly few steps. The notes mention searching 1,000,000 items takes about log base 2 of 1,000,000 comparisons.
Which is only about 20 steps.
Exactly. Compare that to potentially 1,000,000 steps if you had to check every item in an unsorted list, linear search. It's a monumental difference.
That really hammers home the point. Sorting isn't just neatness. It enables fundamentally faster ways to access the data later.
That's the key takeaway. Sorting is often the enabling step for highly efficient searching, querying, and other data operations. They work together.
Well, this has been incredibly insightful, a real deep dive into sorting. We've gone from the simple ideas of bubble, insertion, and selection sort
to the more powerful divide and conquer strategies of merge sort and quick sort.
And seen exactly why sorting is so critical by looking at the efficiency it unlocks for something like binary search.
Absolutely. These algorithms might seem abstract, but they're working behind the scenes constantly in the technology we use. Searching the web, organizing files, databases, it's all built on these foundations.
Understanding them, even at this level, gives a new appreciation for how computers handle information so effectively.
Hopefully, yeah. It's elegant problem solving.
So for our listeners, now that you've got a feel for how computers sort things out, here's something to chew on. What other everyday things, beyond just searching contacts or dictionaries, do you think depend on data being organized efficiently?
Good question.
Think about the trade-offs we discussed, speed versus simplicity or memory usage. How might those factors influence which sorting algorithm gets chosen for, say, your social media feed versus maybe a critical system in a bank?
Yeah, or sorting emails versus sorting scientific data. The context matters.
It might make you look at the digital world a little differently. Thanks for joining us on this deep dive.
My pleasure.